algorithmic analysis of various game theoretic models and has made fundamental contributions to understanding of equilibrium computation in games. Many of his techniques and insights that he has developed span a wide variety of topics in theoretical computer science, including complexity theory, algorithms, and the theory of optimization. He's also very much interested in automated trading, and over the years, he has been actively involved in developing various platforms for trading solutions. His recent work that involves two complexity classes, PPAD and PLS, that are fundamental in algorithmic game theory, won the Best Paper Award in Stock this year. And he will tell us more about this result today. Over to you, Rahul.
Thanks very much, Sunil, and thanks to the organizers. It's great to be here. So I'm going to tell you about the result that Sunil just mentioned. So the paper's titled "The Complexity of Gradient Descent. CLS equals PPAD intersection PLS." So don't worry if you don't know what these three complexity classes are. I will spend over half the talk giving background and context for this result, and at the end give a sketch of the actual proof. So this is about gradient descent, but actually our starting point was CLS. And I'll also, as well as motivating why we would like to think about gradient descent and how we think about it, I will also give a bit of a backstory for how we ended up here. Okay, so this is joint work with John Fernley, who's at Liverpool with me, and Paul Goldberg and Alex Hollander, who are both at Oxford. Okay, so let's start with a fundamental problem in optimization. So we're given a compact domain, so imagine the unit hypercube, and we just want to minimize some function over that domain. You can assume that f is continuously differentiable, but it may not be convex. So this problem is actually NP hard, even for a quadratic polynomial given explicitly. So what people still want to solve this in practice, and one thing that they would often do is apply gradient descent, which is used all over the place across data science, optimization, the physical sciences. So the basic intuition is we're trying to minimize this function, move in the direction of steepest descent. So we see this iterative process here where we're updating x by subtracting from it the gradient. So the reason for the minus sign is we want to go down, and we have a step size that says how far we're going to go. And for this talk, that's just a constant. So here's a little picture. So this is gradient descent being applied to a function from the square to 0, 1. And indeed, the hard instances of gradient descent that we're going to construct by the end of the talk are going to be on a simple domain like this in 2D. But actually, gradient descent is not really solving this problem 1. It's not solving the NP hard problem because it can get stuck in any stationary point. Actually, technically, not a stationary point, but because of the compact domain, actually a Karush-Kuhn-Tucker point due to the boundaries. But in our construction of hard instances, the stationary points are going to be on the interior. There are going to be no other KKT points. So for the rest of this talk, you can just think about stationary points. But if I slip up and say KKT point at some point, this is kind of why. So note that this actually, in terms of solving the original problem, what you actually find could be a maximum. Note that if you actually try to do this gradient descent step from an actual local maximum, you won't go anywhere. So that is actually a solution. Nonetheless, gradient descent often does a very good job in practice of finding useful solutions. So you can think of this talk as being about asking the question and answering it. What is the complexity of finding a solution where gradient descent actually terminates? And we're now going to try and formalize this a bit. So we're going to assume that the input is a continuously differentiable function f on the unit hypercube domain. We have a given step size, and we're given a precision parameter epsilon. And for now, you can assume that f and the gradient are given as arithmetic circuits, and that's going to be used in our main results, but subsequent results have actually looked at other representations of f, and we'll touch on those near the end of the talk. And the goal is to find a point where gradient descent terminates. Let's look at a couple of ultimately equivalent up to polynomial time reductions definitions of terminating. So here's a natural one. So we're defining x prime as the next point. That p should be an f, sorry. And the first one we're going to call local search, gradient descent local search. So we're just looking for a point where we don't get much improvement. So we don't get more than an epsilon improvement. A second one we're going to call GD fixed point says that actually x itself is not moved much. Okay. And you could also think of a third in terms of the gradients being small, and that's also going to be polynomial time equivalent. But these two particular views, the local search view and the fixed point view, are relevant because the complexity class PLS is all about local search, and the complexity class PPAD is all about fixed points. So that's why I highlight these two definitions. Okay, so how might we solve this problem? Well, one obvious way to solve this problem is to run gradient descent. And indeed, when our results came out, lots of machine learning people said, but hold on, you can solve this problem in time polynomial in 1 over epsilon. Why is this interesting? So technically, this is not polynomial in the input size. So as a complexity theorist, we'd be interested in, can we solve it in time polynomial in the input size? And actually, perhaps a better answer to the machine learning people is by the end of the talk, you'll see that the high accuracy stationary points, which we're ultimately interested in finding in this way, actually encode very interesting problems from game theory and fixed point theory, etc. So we're interested specifically in high accuracy stationary points. So running gradient itself is not going to do it. We're going to look at this from a complexity theoretic point of view. What is the complexity of this? Then you can ask, well, is it even reasonable to ask for something that would be polynomial in log 1 over epsilon? And as context, well, yes, if f is convex, then the ellipsoid method would be one way to get that. And so it's what you can think of what we're asking here is what happens when we drop that convexity? Could we still hope to get polynomial in log 1 over epsilon? Okay, so with that problem defined, we're now going to introduce a bunch of other total search problems and related complexity classes, which are going to allow us to answer this question of what the complexity is. So notice that the problem as we've defined it will always have a solution. So the gradient descent problem we have defined will have a solution. We have a compact domain. In particular, we have global optima in that domain. So we certainly have stationary points or KKT points. So this is a total search problem, meaning that a solution is guaranteed to exist. These total search problems have played a central role in algorithmic game theory in finding and classifying the complexity of various problems. And going back even before that, they have often been the problems considered closest to P, but not known to be in P. As one example, and that relates to the fact that they're in the associated decision problems are naturally in NP and co-NP. And so if you go all the way back to the 70s, linear programming would have been one such example. That ended up being in P, but others such as finding Nash equilibria in strategic form games, mixed Nash equilibria, ended up being hard for a complexity class we'll introduce shortly and probably not in P. So we're interested in total search problems. Other examples, so Nash, find a mixed Nash equilibrium of a game. Factoring, so I give you a number and ask you to find a prime factor. Brouwer, so I give you a continuous function from say, the 3 cubed to itself and ask you to find a fixed point. Contraction, the same thing, except I've promised you that the function is actually contracting. So there's going to be a unique fixed point. And finally, pure congestion. So this is finding a Nash equilibrium again, but this time it's not a mixed Nash equilibrium. It's a pure Nash equilibrium in a type of game that is guaranteed to have one, giving you the totality. And finally, gradient descent. So these are all examples of total search problems, but gradient descent on a compact domain is important. Okay, so what do they all have in common? Well, we've just said they're total. But in addition, they're also NP total search problems. So if I give you a candidate solution, you can verify efficiently whether it is indeed a solution or not. That's important because what it means is it's unlikely that NP hardness is going to be a useful way to show anything about these problems, because if one of them was NP hard, then we'd have NP equals co-NP, which is a result of Megiddo and Papadimitriou that dates back to when they defined this complexity class at the beginning of the 90s. In addition, TFNP itself, by the semantic general way it's defined, is not expected to have complete problems. So the way that this went after the definition of TFNP is that Papadimitriou initiated with others the study of syntactically defined subclasses of TFNP that do have complete problems. The first example actually is one where we don't know any complete problems yet. It's a bit of an odd case. And these classes are basically defined by a proof principle that ensures the totality. So one such proof principle is the pigeonhole principle, and that gives a class PPP where we don't have complete problems. A second one is PPA, which is based on a graph theoretic parity argument. And we do have a complete problem there. For example, the Borsuk-Ulam theorem and other problems in computational social choice more recently have been shown to be hard for this class. Complete, in fact. Then PLS, which is a local search class, which has complete problems such as the pure congestion game problem that we just mentioned. So find me a pure Nash equilibrium in a congestion game. And PPAD, which sits within both PPP and PPA and is a directed version of PPA. And for that, we have complete problems like Nash and Brouwer. Factoring is placed in this slightly odd position. We have randomized reductions that place it in PPA and PPP. And so, but it would be really a big result to de-randomize those. Okay, so what reasons are there to believe that these classes are not equal to P? So many seemingly hard problems lie in these classes, like some of the ones we've just described. We have oracle separations between the classes, in particular separating PPAD and PLS. And we have a range of hardness results based on cryptographic assumptions. So we generally believe that these classes are not easy, and that if you show hardness for them, then that problem is not likely to be in P. And our gradient descent problem lies in PPAD and PLS. So if we actually zoom in and now just focus on PPAD and PLS, we see that our fixed point definition of the problem puts it in PPAD. So a fixed point of this function that takes us from one point in the domain to another via the gradient descent step. It's a continuously differentiable function, so we can then apply Brouwer's theorem on that, and we have a fixed point there. And our local search definition puts us in PLS, so we're actually in both. Okay, so Daskalakis and Papadimitriou spotted that actually quite a few problems that had been open for a long time, things like the simple stochastic game problem, P matrix LCP, mixed Nash of a congestion game, they all lie in PPAD and in intersection PLS. So this was in their Soda 11 paper. So they started studying PPAD intersection PLS. They noted that contractions in there, mixed congestions in there. And the P matrix LCP, don't worry if you don't know what that is, it's not that important. They actually decided for one reason or another that PPAD intersection PLS is likely not to be the right class to classify the complexity of any of these, and I'll explain why now. First, I just want to explain why one should then stop looking for PPAD hardness or PLS hardness for any of these problems once they lie in the intersection. And that's because we do not believe that either of these classes is contained in the other. So if a problem is in the intersection, then if it was PPAD hard, then PPAD would be within PLS. And if it was PLS hard, PLS would be within PPAD. So we just do not believe either of those is true. So instead, rather than looking for PPAD hardness or PLS hardness, the next thing to consider might be actually PPAD intersection PLS hardness. And this seemed unnatural to Papadimitriou and Daskalakis, and to us too. So it was a surprise when we got this result. And that's for the following reason. So suppose that a problem is A is PPAD complete and another problem B is PLS complete. Then the following problem is complete for the intersection. Either AB takes two instances, one of A, one of B, and asks for a solution to either. These can be totally unrelated. You take any instance of a PPAD complete problem A and any instance of a PPAD complete problem B, totally unrelated. This seems quite unnatural. So at that point, they actually dismissed this class. And let me give you a concrete instantiation of either AB using PPAD and PLS complete problems to motivate what they went on to do, which was define CLS, which was the other class mentioned in the title. So we're not yet at CLS, so let's consider either Brouwer or local opt. These look a bit technical. The main message will be on the next slide that what Papadimitriou and Kostis did was they combined these definitions from the either setting to a kind of combined thing that had not independent functions, but a single function in a sense. So for Brouwer, you're given this function f from the cube to itself, and you're asked to find an approximate fixed point. That's PPAD complete. For local opt, you're given a potential function, so from the cube to 0, 1, and a non-continuous function that takes you from one point in the cube to another, so that you can think of this as a neighborhood function. You're again given a precision, and you're asked to output a local minimum of P with respect to the neighborhood function, meaning a point X such that by applying G, you don't get an improvement in P, or you don't get much of an improvement in P. Okay, so this is an example of a PPAD intersection PLS complete problem. And the key thing to note is G and F here are totally independent. And so what Kostis and Christos did was they defined continuous local opt in their SODA 2011 paper as something that actually takes the G that we just saw, okay, takes the G that we just saw here, which was non-continuous for this to be a PLS hard problem, and actually makes it a continuous function f. Okay, so CLS is now all problems that can be polynomial time reduced to continuous local opt. This was how they defined the class. And they placed a bunch of problems in CLS2, as we'll see now. Stepping back for a sec, so PPAD is all problems that can be solved by path following. PLS is all problems that can be solved by continuous local search. CLS is all problems that can be solved by this continuous local search. And now maybe you already get a sniff that actually gradient descent just has a very specific F here in a sense. So it's also natural to ask, and this is how we ended up there, in investigating CLS, we noted that some of the problems that Daskalakis and Papadimitri had put in CLS, they did so by applying essentially a gradient descent argument, which is what got us thinking about this. And so you can think of a class GD in this context. So now let's look at a picture. So we've got PPAD intersection PLS, where we have complete problems like either Brouwer or local opt, and then CLS, which has its canonical complete problem, continuous local opt, and then a bunch of other problems, all of the ones I've mentioned so far, within CLS as well. So we didn't at that point have problems that were in PPAD intersection PLS, but not known to be in CLS. The problem was, for a good few years, we had no complete problems for CLS other than this canonical one, though. And that was remedied in 2018 by a result of Kostis, Zamos, and Zampatakis, who showed that a version of contraction where the metric is actually part of the input to the problem is CLS hard. I consider that rather unnatural, though, because for the actual contraction problems that we're kind of interested in, so for example, for simple stochastic games, and many other problems where you may be interested in contractions, the metric is something like an LP-induced metric, induced by an LP norm. And so, for example, for SSGs, it's just the L infinity norm, induced metric. And so for Banach, this problem Banach they've defined, they're actually allowing an arbitrarily complex metric defined by an arithmetic circuit given as input to the function. And that is very, very powerful. And as we'll see, I mean, it possibly takes you far away from the contraction where it's an LP-induced norm, but that's an open question. So anyway, we didn't have any natural complete problems for CLS, I would argue. And gradient descent also sits in here as a special case of continuous local opt. Okay, so that was the state of play before our results, apart from the fact that we were the first also to kind of highlight gradient descent as a distinct problem. And our main result is actually a collapse that says, actually, gradient descent is not only hard for CLS, gradient descent is actually hard for PPAD intersection PLS. And so we get a collapse like this. Actually, PPAD intersection PLS is equal to CLS. And all of these problems are complete for it. Either solution AB, continuous local opt, Banach, and gradient descent. And we'll come back to some of the open questions and ramifications of this later. The main next section of the talk will be sketching this result. Okay, so gradient descent is PPAD intersection PLS hard. The way we're going to do it is we're going to reduce from either AB, where A is the PPAD complete problem end of line, and B is the PLS complete problem ITER. Don't worry if you don't know these, I'm going to be sketching them. And one other thing, so we've gone from gradient descent being PPAD intersection PLS hard to actually 2D gradient descent. So we managed to do this with a 2D domain, and that actually resolves some ambiguities and uncertainties around CLS too, and shows that CLS is essentially robust up to the definition of the domain all the way down to 2D, where in the paper they defined it with 3D and some general dimensional versions, and there was a bit of uncertainty there. So this is the main result, a reduction from either end of line or ITER, a PPAD and PLS complete problem respectively, to 2D gradient descent. So I'm going to sketch the proof, and the basic idea is that we have a domain, namely the square 0, 1 squared. We overlay a grid on top of it. So we're going to overlay a coarse grid that's going to allow us to embed a higher level PPAD complete problem. And then fixing some of the issues with that, we're going to have a finer grid where we insert a kind of PLS gadget as well. On that grid, what we need to do is we need to assign values for the actual height of the function and the gradient of the function. We're going to do that on grid points. And then to finish the reduction, we're going to use bicubic interpolation, which is a very nice method that literally allows us to specify exactly these points, the height and the gradient, and then interpolate in such a way to produce a smooth function that agrees with the heights and gradients that you specified. And what we need for the reduction to be correct is we need that at the end, all stationary points are either solutions to our end of line instance or they're solutions to our ITER instance. So in order to kind of organize the pictures and describe the construction, we're basically going to have use these colors and directions. So the left part is essentially different height regimes. So black is going to be medium height in the middle, and that's going to be the default height. And it's going to have a corresponding direction of improvement, meaning going downhill is going down and to the left, which is going to be towards the origin. I'll show you a picture in a sec. And then the interpretation here is orange things are above all black things. Red things are above all orange things. Blue things are beneath everything else. So these are actually classes of heights, and these are actually the directions of improving, meaning going downhill. Okay, and so we start, before we even get to embedding our PPAD or PLS problems, we're starting with just a default background. So on top of 0, 1 squared, we're going to stick black everywhere to start with. So these are all pointing down towards the origin. And so on the right, you actually see this plane going up from 1, 1 down to 0, 0, just a flat plane, everything sliding down towards the origin, which would obviously give you a unique solution here at the origin, and we're going to fix that. How we're going to fix that, I will first need to introduce the PPAD complete problem that we're going to introduce and reduce from. That's end of line. So end of line is the following problem. We're given a directed graph with in degree and out degree at most 1. Because the in degree and out degree are at most 1, it's a collection of paths and cycles. I don't have a cycle in this picture, but you can have cycles in general. You are guaranteed that vertex label the vertex with label 1 is a source. Because you have a source, and the thing has in degree and out degree at most 1, so it's directed paths and cycles, you therefore have a sink, in this case 8. You may have other sources and sinks like 7 and 3, but you at least have one sink, namely 8. And your goal is to find any source or sink other than 1. Okay, so in this case, the solutions would be 3, 7, and 8. 2 of them are sinks, 1 of them is a source. Okay, the catch, of course, is if I gave you this graph explicitly, this problem would be easy. The catch is that the graph is exponentially large because it's encoded succinctly by circuits S and P for successor and predecessor. So Papadimitriou came up with a nice simple encoding that, that with these 2 circuits defines this directed graph with the required degree properties. And so we want to embed this problem in our gradient descent problem, along with the PLS problem that we'll come to afterwards. And so what we're doing is at a higher level, we're starting with the PPAD complete problem. And then later, we're going to use the PLS complete problem to fix some issues. So here's a picture. It's corresponding to the instance, the end of line instance that we saw on the previous slide. So we have stuck the vertex labels along the diagonal. And the first thing to notice is we have a path coming out from the origin. So that's the thing that's going to fix the fact that otherwise we would actually have a solution at the origin. So you can think of everything coming down towards the origin. But then at the start here in the bottom left, we're going to carve out a valley, which is essentially a new path for gradient descent to follow. And it's going to follow that along the green lines. So why are there green and orange lines? Well, the green lines are going across and up between two vertices whenever the vertex index goes up. So notice we're capturing all the directed edges in the graph in this picture. So we go from 1 to 4, we go from 2 to 8, etc. The ones where the vertex index goes up are beneath the line, the diagonal, and in green. The ones where they go down are above the line and dashed in orange. So I'll explain how we came up with this, because it may look a bit weird. There was actually some historical precedent here in a sec. But the key thing, one key thing to observe right away is, back to our value diagrams, these orange things are above the kind of default background. The green things are below it. And both of them we're improving as we go to the right and up. So that's why I've done the orange lines dashed, because they're actually going in the opposite direction. So here you see that the line goes from 7 to 3 in the end of line graph. But actually, in terms of where gradient descent is going to take us, we're going to kind of go the opposite way along that edge. So what have we actually achieved here? Okay, and so sorry, one sec. For that historical precedent, how we actually came up with this was, Hubacek and Yogev have a nice paper from Soda 17 where they showed essentially lower bounds for CLS. So they created a problem called end of metered line, and they showed lower bounds for it, and separately they showed that it was in CLS. And the way they showed it was in CLS was essentially the green line construction. So they had already had some kind of construction with a very special end of line graph where numbers always go up. So they had that property. And then they did the green stuff. It's all locally computable. They also needed to do some interpolation, but they did a different type of interpolation to us because they didn't care about the gradients at all. And so, you know, we're going quite a step further in numerous ways, but they'd already done some key parts of the story, namely to embed this thing in a continuous way, ignoring the gradients, as long as the numbers went up along the line, along the end of, as long as all of these paths were monotonic in the end of line instance in terms of the indices. Okay, so we've also added in these orange things, and let's now have a look at where these paths start or end, which are going to be stationary points at the moment. And we notice that they end at 8, end at 7, and start at 3. And so those are going to be minima and local maxima respectively, which is absolutely fine, because those are indeed solutions of our end of line instance. What's the problem then? Well, the problem is at points where green meets orange. So where green meets orange, it's not hard to see that there's no way to escape having a stationary point. So you've come above, you've come below, somehow you need to reconcile this thing, and there has to be a stationary point there. And so that is where the PLS part of the either comes in. So there has to be a stationary point in this box, here and here. Somewhere there has to be a stationary point. We take advantage of it. And so what we do is we actually stick a gadget that we call a PLS labyrinth inside these boxes, such that once you're there, the stationary points that exist in those boxes are solutions to the other problem, ITER. Okay, so let me describe the ITER problem briefly. So this is a PLS-complete problem. It's again defined by an exponentially large graph that's encoded now by a single circuit C, where C is going to tell us where to go to, which could be actually a self-loop, but it's always actually pointing to a higher numbered vertex. So edges point to the right. So we've ordered all the vertices at the top, as you see, 1 up to 8. And edges point to the right, or they can be self-loops. And we're asked to find a vertex that points to a self-loop. So that the reason that 3 and 7 are solutions here is because 3 points to 6 and 6 is a self-loop. 7 points to 8 and 8 is a self-loop. Okay. We didn't define this problem. This problem was known in the literature. It was just convenient to work with. The kind of one key intuitive difference between PPAD and PLS. In PPAD, you could pick a random vertex and just start there, but it could be on a cycle. So you can certainly follow the graph around, but if you don't know that you've started from an equilibrium, for example, the source that they've given you as guaranteed in the input, you can't guarantee that you'll terminate. Here, you can essentially start anywhere that has an outgoing edge and follow the path. Okay, and so that already gives you some sense of how PLS and PPAD are really quite different classes. PLS can be thought of essentially as finding a sink in a DAG. Okay, and so what we're going to do is, so if you look here, this is now at a finer resolution than the big picture we were looking at. In particular, if you look at the bottom, we have a green path coming in and this orange going across.
A quick question, Rahul.
Yeah, sure.
Is this graph also going to have a out degree 1?
This graph, each thing has out degree 1, but it may have multiple higher in degree.
Yeah, okay. So out degree is 1. Okay.
Yeah. Okay, so if you look here, we're actually now reasoning about this particular PLS box. There's another one that is kind of symmetric and flipped, but we're coming in, see green at the bottom and orange across. And so the picture we're seeing here is kind of zoomed into that PLS labyrinth. And again, the orange is just indicating that actually we're descending, going to the right, because if you go back to our picture, we see that orange gets decreases, meaning improves the objective function in this top right quadrant, so going to the right or up. So we're improving as we go along here and as we go up these paths. And the basic idea is we are going up to the diagonal, which we've labeled 1 up to 8 in a similar spirit to before. We're going up to the diagonal whenever we have an outgoing edge from the corresponding vertex. So for example, we have an outgoing edge from 7, so we go up. But we don't go anywhere afterwards, and we're going out from 5 once we've gone up to 5, given that there's an outgoing edge, we then connect it to the 7 path to represent the fact that 5 goes to 7. This creates what turns out to not be an issue, but this creates the fact that paths actually clash, and that's actually okay. We just merge into the ones that go straight up, that take priority, and restart on the other side, which is actually okay given where blue is in our value regimes. We don't introduce a solution there. And so we end up with solutions at 3 and 7 exactly as needed. So I appreciate that was a bit quick. The main thing to take away is, okay, and this is a little picture that shows how we actually construct these things with the fine grid, giving kind of directional arrows and heights to all these things, where these would all get little numbers next to them. And then we have to prove that when you interpolate, all of these squares don't have any fixed points, don't have any stationary points where we don't want them. So the high level picture here is, what we've done is all the stationary points are either solutions to end of line, shown here in blue, or they're inside our PLS instances in the PLS labyrinth, so they're solutions to the ITER instance. So that completes the somewhat quick high-level sketch of the main result, and in the rest of the talk, I want to discuss the implications. So first, a recap of the main message. So actually before, PPAD and PLS were both successful classes independently. PPAD exactly captured the complexity of finding fixed points and Nash equilibria in certain games. And PLS exactly captured the complexity of finding local solutions to various NP-hard problems like max cut or the traveling salesman problem, and under suitable neighborhood definitions, and also certain problems in game theory like local max cut. PPAD intersection PLS was known to contain a bunch of interesting problems whose complexity was wide open, but it was not believed to actually be the right class to capture the complexity of any of those. In particular, it was not believed to have interesting complete problems of its own. And CLS was introduced as a natural, presumed distinct counterpart. And now we see that PPAD intersection PLS is a natural class with complete problems. In particular, it captures gradient descent. PPAD intersection PLS is equal to CLS. And now there are many problems that one might try to show PPAD intersection PLS hard. So in particular, some of the most natural ones relate to our problem defined the function as an arithmetic circuit. What if you wanted to represent the function using, say, an explicit polynomial? So that's a very natural question. Another one is, I told you about pure congestion. So where you have a congestion game, finding a pure equilibrium is PLS hard. It turns out that finding a mixed Nash equilibrium of a congestion game is in PPAD and PLS, because a pure equilibrium is a mixed equilibrium, which is kind of why it's in PLS. And the fixed point property of mixed equilibria make it also in PPAD. So actually, it happened that Yakov and Aviad had a reduction from KKT to mixed congestion via degree 5 polynomials ready to submit to the same stock that we submitted to, and found out about our result about a week before and quickly adapted their stuff to get PPAD intersection PLS hardness for these two problems. So let's just dwell on that for 1 sec. So we have arithmetic circuits, but we're in dimension 2 for our result. They have polynomials, but in arbitrary dimension, but with degree 5. And that's where we are at the moment. We'd like to get that degree down for the explicit polynomials, and that's something we're working on. Other problems now are contraction, which we've already talked about, but also Tarski. So Tarski was a problem that was shown to be in PPAD and PLS by Aviad, so Rubinstein, Papadimitriou, Yannakakis, and Etisami in alphabetical order. And they'd shown it in PPAD and PLS, but not done, but asked, is this in CLS? It just wasn't clear. And now, of course, our result shows that just by showing independently that something's in PPAD and PLS, you get that it's in CLS. And so Tarski fixed points, which also have important applications in game theory, Tarski fixed points are now a potential candidate for PPAD intersection PLS hardness too. And another similar example is colorful Karateadori, where we had independent proofs of PLS and PPAD membership, and now we know that actually it's in CLS and can be solved by gradient descent, etc. Okay, so that's all I had to say. Very happy to take some questions if there are any.
Thanks, Rahul, for the wonderful talk. We have time for questions. So if you have questions, you can raise your hand or type in the chat box.
So, I mean, I'm just trying to understand, Rahul. I guess, so the grid is exponentially fine to encode an exponential size graph, right?
Yes.
Inside each grid, diagonal grid cell, again, you put an exponential sized instance of, because the PLS graph also, the ITER problem also has.
Correct.
right?
Correct.
So the fact that you use the same 8 was a coincidence. It's not, I mean, without loss of generality, you can do that.
Yeah, it's a coincidence. Yeah.
Okay.
Just think the thing's exponentially wide and tall, and that's all that really matters. But you need that, yes.
So and somehow, I mean, I guess there's a number issues. Those are all okay because the bit length is roughly n or something.
Yeah, roughly, yeah.
Okay. Okay, thanks. I just wanted to kind of get the construction clear a little bit.
So can you say something about these pairwise separable games? For instance, maybe coordination polymetrics games, is it known to be PLS intersection PPAD hard?
Great question. Okay, good. So we can go back to the last slide and continue what I was saying there. So it happens that the network coordination, which you could also call team polymatrix. So a polymatrix game is where players are nodes in a graph. The graph is encoding interactions between the players. And then on any edge, you have a bimatrix game. So a two-player game between the endpoints of the edge. Now, you have the restriction that all bimatrix games that are incident to a particular node have the same number of strategies, because that node is going to play a single strategy in all of those games, and they're going to get the sum of the resulting payoffs that they'd get from these individual interactions. So it happens that it's not hard to show. So that problem also featured in the CLS paper, the original one. And it's not hard to show that reduces to mixed congestion. They didn't observe it in the CLS paper, but it's not hard to show that. And actually, the end goal of Yakov and Aviad was to get all the way down to network coordination. And roughly speaking, if they'd got the degree of the polynomial down to 2, they'd have succeeded, but they only got it down to 5. You can think of the degree of the polynomial being 5 as roughly being, we have something like a network coordination game, but now we have a hypergraph where 5 people are interacting, where they only want 2 to interact to get all the way down to network coordination. So it's an excellent question. It's the natural continuation of some of this work to resolve these open problems. It's probably one of the biggest open problems that I could add to this list. Yeah.
Thanks.
But that's directly related to the other open problem that I'd already mentioned, namely getting the degree down in the polynomial.
Right. Yeah.
Yes, I saw a hand.
Jay Kumar. Yeah. Jay Kumar.
Yeah, I'm just trying to understand how the construction worked. So I thought at the course level, the first set of lines that you drew, they came from PPAD.
Correct.
But if you just left them as it is, you would probably get some spurious fixed points, which now you are trying to guide into some PLS solutions by putting that second level graph there.
Correct.
Is that roughly?
That's absolutely correct. And to expand on that slightly, it's also crucial that for our PLS labyrinth to work, we need to have the blue and the green and orange lines meeting in the way that they do. So we can't just introduce those PLS labyrinths anywhere, otherwise we'd get PLS hardness. So we can't get PPAD hardness, we can't get PLS hardness. So there's a bunch of conditions on where and how these things could interact. We take the approach of having PPAD hardness at the higher level and introducing those PLS ones at the lower level, but you could imagine trying to do it the other way or various ways. But what's certainly true is where we introduce those PLS labyrinths, you need the properties that, both green and orange are meeting here. You can't, for example, introduce one here.
No, but the second level, you introduced a little PLS picture inside a big grid. Now, you couldn't reinsert a PPAD picture there, and then it would become either, so there must be something which is special about PLS, which allows you to use that and not just another PPAD.
That there is. I'm not sure it's easy to crisply extract what that is. It's just the fact that if you could insert a PPAD one, we'd get an unexpected result.
I understand.
We worked hard to introduce the PLS one, but and you're correct, it shouldn't be that we could just introduce a PPAD one there.
So, okay, so PPAD allows you some features which sort of complete the solution for you rather than leave loose ends there too. Right?
Yeah, PLS, I think you meant. Yeah, PLS allows you here to end up without anything spurious, just ending there with exactly what you want.
Thank you.
And this is how, I mean, so what several complexity theorists, I'm not really a complexity theorist, but what several complexity theorists have asked me immediately is, so when are we going to show that PPAD equals PLS? I actually don't believe they're equal. I believe this is now a genuinely interesting class where PPAD is not equal to PLS and the intersection is interesting independently. Yeah, I suppose it's another open question is, are there other examples like this?
Yeah, so I guess, what is the implication for machine learning? I guess it's the precision is the issue.
Yeah. To put it in its most blunt, harshest form, Costas would say this regime is no interest to machine learning at all. Which is kind of true, right? I mean, they're really not interested in getting this high accuracy stationary points, and that's another way to think of this. I mean, we can encode game theoretic solutions like mixed Nash equilibrium congestion games as stationary points, but with exponential accuracy. And yeah, that's interesting for us, but not necessarily for a machine learning person.
Any other questions? Okay, so then on behalf of everyone, I thank Rahul again for this wonderful talk. And this is the final session of the conference, I believe. So maybe Chandra or Nikolai, you want to say a few words?
Yeah,